pivoting axis going into and out of the paper, and then the distance to that is 3 m. So the other moment of inertia that you'll be using is for the beam.
These are in the data sheet.
So this beam here, it says in the question that it is a rod. So if you look at your data sheet, so this one seems to say rod. But if you look at the rod moment of inertia, it requires you to put in the radius of the rod. But in the case of this question, there isn't radius. So that's why we'll take this moment of inertia. Unless you're given the radius, so you can fill in this r over here. But because there's no radius that's given, it's only the length. Then no matter how they describe it, might it be a rectangular, square, or circular rod, then we'll make use of this case. So this one is a bar. Right? Okay, it's a bar. So the moment of inertia for that bar is 1/12 ml squared. So this mass will be the mass of the bar. So in our case here, the mass is m. So sometimes this beam may not be m, but 2m or 3m or half m. So respectively, you put whatever m for the mass. And the other thing is L. So note that L is not where you pivot. It has nothing to do with pivot at all. It's the entire length of that bar. So in the case of this one over here, it's the entire length. So that one would be 4L. So it's not just 4L, but 4L and then there's a square. Okay. So those are the two things that we'll be making use of. So the first one, the moment of inertia for the beam. Right. So that will be equal to 1/12. So it's ml squared, so m is this m. And L will be the entire length, independent of this pivot. That will be 4L squared. Okay. So the other moment of inertia, that is for this point mass, and I think it's called additional mass. So indeed, I'll use M to indicate that. Maybe have the letter, that you know which one I'm talking about. So for that, okay, there's one thing that I missed. So, because the beam is not pivoted right in the centroid, so if the beam has been pivoted at the centroid, then you would use this over here. But since the beam is not pivoted at the centroid, it's pivoted at somewhere over here. Right? From 3 length to 1 length over here. The centroid of it is over here. So this then would be 2L, and that one here will be 2L. So if it's pivoted over here, that means that way. Then we can use this 1/12 ml squared. But since it's not, and we have to see how far away is it from the centroid. So in this case, the pivot is actually L distance away from the centroid. Right? So because of that, then we have made use of the para-axis theorem. The para-axis theorem says that if it's not over at the centroid, it's CG, the centroid. If you move it to that actual pivoting point, let that distance be h. then you need to add over here m h squared.
Okay.
So we need to add that to the next one. M and h in our case here is L, so ml squared. So we have that plus ml squared.
Yeah, I know.
So if you do that calculation, you should get 703 ml squared.
Let's keep searching.
So for that item, that will be the mass multiplied by its distance away from the pivot point. So over here it will be 3L, so 3L squared. So if you work it out, you will get 9mL squared. So the total inertia, right? And I use not to represent it, it will be IB plus IM. So you get 7/3 ml squared plus 9mL squared. So if you're here is able to get this, then you can award him or her marks. Yeah, mark or your friend marks. In whichever color is fine.
Then myself just mark the whole question full on this one can solve everything.
So if you have here got one of these right, one of these wrong, then it's 1 mark. Yes, sir. Subscript, it can be anyone. You can label it in the way that you want. So I'm not that strict about your subscript, what you will label it, that's fine. So now that you have that, then let's have a look at the free body diagram. So for the free body diagram, I think there's going to be a few variants. If your peer were to write the free body diagram in the following way,
Yeah.
alright, if your peer were to write free body diagram in this way, please mark wrong. Because this is a schematic diagram, it's not a free body. Besides writing this, if your friend were to write the following thing, that is a free body diagram, and the free body diagram, please see how I sketch it. You're going to have that other point, and then this point over here is a point O, so refer to this, this is one point O. And I'm going to go into dynamics and then straight away. Right. And then you have your forces. That's for the spring force. And then your bending force somewhere here. Right. And then K, L, it can be sine here or here. So if it's clear, if your friend didn't write for small angle theater, then there'll be a mistake. Okay? So you can help your friend to write down for small angle theater. Okay? So you know how strict we are looking at it. So if he or she didn't write this, and then wrote sine theta, then it's correct. Right. But once you write theta, then you must say that generally this theta is for small angle theta. And then for this part here, that big force C multiplied by 2L theta delta. Right. If your friend wrote this as KLX C2L X dot, please mark that wrong because this is a rule for resistance. Yeah.
Wait, which means you draw where you still can prove what? If you draw
And then there's this angle
correct, technically.
theta. So if that angle theta is written in this way, you can see it's conflicting direction. Then please mark them wrong. Yeah, but only if it's written one side without the other side, and if it's in the correct direction, then it's correct. So in this case, this arrow must be that way. Right? So the whole beam is rotated.
Ben. Ours is like that, right?
So if your friend wrote down the mass over
And we
here
still managed to prove.
and no forces, then it's correct.
Because your Twitter going down.
But if there's mass over here and
See the Twitter going down.
That's going down.
right, provided there's no forces,
Why?
then you'll be correct. If your friends start with static condition, then you will work out, there'll be that forces. Eventually, we'll still be canceling that. As long as the shown form is correct. Then.
Where is the small m?
So we have already kind of like moved on from static condition. So in dynamic condition, we don't write down the mass over here. Right? So it is possible. So if your friend look at this, and the pivot point is here, but kind of wrote it in that way. Yeah. That means, right? Do you see the difference? This one and this one, and wrote that way here. But this one is wrong. Yeah, because it doesn't rotate that way. This is not the pivot point. Okay, so it's still okay. I'll be looking at how you formulate your equations later. Yep. You mean this way? Yeah. This way is also okay, but actually, yeah, so all the signs are reversed, but actually, there's an indication of angle over here. So, while it's not entirely wrong, it will still be marked correct, but it's actually easier, so you deal with less negative signs. Correct? So, please make sure you follow. Okay? Any other different kind of working with the scene of your friend?
No, he said that one can, but then you need to reverse, but there's already indication. So there's
Can, just what makes it sound.
Never mind, you very late, it's okay. You haven't understood, right?
This way? And in this way? This is incorrect.
They never said the theta, then you can assume.
There's no angle here. This is
But they managed to
dynamic.
prove it. They
So
managed
it
to
must
prove.
prove.
They do opposite.
It's not static.
They managed.
If it's static, then you'll be this way. And then you get your forces. Yeah. And then there wouldn't be damping force that's coming in. I think this one is upward.
They managed to prove.
So now that you have all these forces, then we go about formulating the second order differential equation. So we have this up here, minus AL here. Oh, by the way, if your friend wrote down this and then multiplied by L here, right? Because over here is this, yeah. So this is force. This is perpendicular distance, right? Then you get moment because we're gonna sum up moment around point O. Yeah. So if this force over here is written as a moment, then please mark your friend wrong. Right? It wouldn't be this. It's only the force. Right? So there was 1 year that the student got 99 marks, yeah, 99 upon 100. And that 1 mark that he lost was from here. Okay? So I just want you to know how I will mark. So this is not moment, but this is force. So all these, they are forces. They are forces. These arrows here, they are forces. Okay. So the other force is also in the opposite direction of our convention. So minus 2L C here dot and multiplied by 2L 2L.
Ben, why
Is from here to here.
times length theta?
This
Perpendicular
is
distance.
L. From here to here.
What is it? What?
The first one, right? Minus k
This is L.
length theta. Why
It's
is it
actually
times by length
2L
theta? Okay.
cos
Isn't it times by
theta,
length
L
theta?
cos theta, but because you wrote
Distance.
this down, you don't have to be bothered about that.
Or is it
So
here?
it's very dense way.
Sin theta for small theta equals to theta. So to get the moment
So that takes
is
care of
L
the
sin
two.
theta.
Then he never put the sign there.
And then the
Sin
whole
theta
thing
equals to
equal to
theta for
I
small theta.
naught theta dot. So obviously this I naught is what we solved up there. This is my I naught. So I'll put that one in and do a little bit of simplification. So I'll have that 7/3 ml squared plus 9 ml squared here dot dot plus this is 4L squared liter.
It's not L theta, it's theta only.
But this one don't have liter
Don't have theta lah.
because this should be the
Sin
cosine
theta,
here.
cosine theta.
So this
Cosine
will
okay.
He put theta lah. Just
indicate over here.
theta over.
So
Square box.
this and then plus
Cosine theta equals to 1.
CL squared here dot equals 0. So we can adjust everything by dividing it throughout by this coefficient. So you get here dot dot plus 4C over 7/3m plus 9m here dot plus K over 7/3m plus 9 capital M equals 0. Shown.
So you left out a t.
So if your friend is able to get that, then please support them with free quiz.
So you left out a theta, so the k over
There's
The one is
one
without
mark
theta, right?
that will go into
Sir, your
Hey,
teacher's
got no
missing.
tutor.
This part here,
Sir, Sarah, stop, sir.
body diagram one.
Raise your
Sir,
hand.
your teacher is missing, sir.
So altogether, here,
One more try.
7 marks.
Sir, the teacher is missing, sir, from the third one, the K over 7 third M. We are missing. Me. Wow! Under the light. I need a brighter light. Next time I shine torchlight, sir. So you are missing out the teacher, sir. There's a teacher missing. From the equation.
Right?
Yeah.
Over here, right?
Yes, sir. And Shiba also missing.
Right, so if your friend kind of sketched this correct and didn't include this first line, didn't include second line, and then shown, you can write down there, incredible. So what's going to happen is that I get this a lot during exam. So if student didn't write down the step by step, at least this step, the first step, then they lose the mark, and I don't believe that you can actually show it. Right? So you lose all marks. Yeah. Because you can't write down what is already in the question paper and say, show it. I would know. I've also seen students that wrote this down first and then try to work backwards. Yeah. I can see that because you wouldn't have the expanded terms. So those will lose the mark, this and that. So what that means is that just do your understanding, work it out. So you need to have those steps. There's no way that you can get to the short form without the free body diagram.
You didn't include
without
the
this
initial
first form.
condition.
no need. Initial no need already.
I got it.
Why don't you?
He already said he will skip the initial condition already, but he can go straight to dynamic.
So altogether,
No, but if
this
you
is
see
7
the
marks.
small teacher and all,
Yeah,
you have to write down.
You never write.
unless you tell me you can see without.
Any other variants out there? Because you can consult so that you will know how many marks you will get during exam. I can tell you how I mark. Okay. Yeah, so you'll probably still get back issue. So if you sketch in this form, that way, right? And then finally, it will be plus, and then this will be minus everything. You still get back to the short form with your mark, right? Yeah, so if you do it this way, then your arrows will be in opposite direction. But please follow this convention, right? Please follow this convention because I actually make an effort to tell Glasgow in the exam paper if they forgot about this. I actually make an effort to say please indicate the direction of the leader in your application. So why I do that is because so that there's more consistency for everyone. So please look out for this sort of thing.
Got a feeling this will be out for exam.
So the next part says that there's an initial displacement of theta naught.
No longer bring the big laptops, huh?
And the system is free vibration.
We used to bring this big Lenovo laptop.
These are very important keywords.
Rich kids.
So it says that it has this decay decay to 30% of their initial value after 3 full oscillations. So if I were to sketch that, and this sketch has no marks allocated, just for your understanding. So if I were to sketch that, so the sketching, some students just now were asking me, is it sketched this way, or this way, or what else, or this way? Which way is it? Where's the 0? Is it 0? Where is it? Well, if you look at your data sheet, so I only talk about this one time. Yeah. This one is for the simple harmonic motion. Although it's written here 1 minus 1, it need not be 1 minus 1. Right? It depends on the value of k value. There's no empty coefficient because it's simple harmonic motion. So it depends on the value of k, the mass that's involved. Then this may not be 1, it can be 10 or 15 or whatever, but it will be equal to each other, one positive and one negative. So this simple harmonic motion. For this case over here, it starts from 1 and then it goes about in that sort of oscillation and then finally becomes 0. So what it actually means is that this is a case where there's no mass. There's no mass that's attached to it. So it's actually a free vibrating string. Right? So after you lay it down, this point here is where we call 0. And if I were to stretch it past that 0, that stretching displacement, right? You can help me to stretch it so that I can do that. So this is 0 point, and you need to stretch it downward. Okay, this much is your theta naught. Okay? So over here, that theta naught is written as 1. So it need not be 1. It can be any theta naught. So you stretch it, and then when you release it, and you oscillate, and then you do this. Right? This is for free vibration. And then today, we talk about the case where we have a mass that's added. So a step input, and then if you look at the kind of graph that we have, it looks again a little bit different. Okay. So that kind of mass that you have. Alright, so this is a point that we call it 0. Okay? So if I drop a mass, let's say if this thing is a little bit heavy, so if I drop on it, so just now it used to be over here. After I drop the mass, and it drops further. So this has been extended by x. Right? Using Hooke's law, F is equal to kx. F equal to kx. So using x as the subject, x will be equal to F divided by k. Right? So that amount that has been extended is equal to F divided by k. Yeah, can understand, right? So just now it was 0, there's a mass included, and you will drop down even further, and that extension is x is equal to F divided by k. So this F divided by k is over here. Right? That is where it becomes a steady state. Even though it's written as 1 over here, it depends on the spring constant, all this is not necessarily that it's always 1. But we know that it's always F naught over k. So now that you have it, now this is a new position, F naught over k. Now I extend it down, or curve it down, and then I release. And then you will oscillate. So that amount that you oscillate That's actually my phone. Okay, so where am I? So this is the f naught divided by k. So if I were to point down, that is where I start from 0 over here. Right? So this you gotta point down. Okay. So just now, if I don't point down, it was over here, and here is known as f naught divided by k. If I point down, this point over here, I point 0. I call this point my mu 0. And if you were to release, then you will oscillate, and that's the motion that you are seeing. Okay. So this covers all the graphs that you can see from few classes that we have.
Okay.
So it answers, is it this, this? Yeah. So it depends on the case that even you. Is there a mass there? Is there free vibration? So in the case of free vibration, so you start from greater naught,
Right.
and then you oscillate.
Because they start from like that, ma.
Correct? That way.
If you stick from like that, is from the original bottom one.
And what you need to know is that at all this time point over here, this time, not distance, yeah, this is not distance, this is time, is tau d. And this is tau d, and all these are equal to each other, tau d. So it says 3 complete oscillations. So you get a count from here. There's 1 oscillation, there's 2 oscillations, there's your 3rd oscillation. So at the 3rd oscillation, this amount over here, this is 0.3 times of beta naught. That's what those words mean. So after 3 complete oscillations, it would decay to 30% of the initial value. So obviously mine is not scaled correctly, but this 30% of beta naught. So there were that year, one student was asking me about this question. I think he was reading this and then was asking, Prof, this one, is it pi or 2? This is English. I also explain. Pi means it go until there, this is 30%. 2 means that this part here is 30%. Do you understand? Yeah. Decay by 30%, decay to 30%. Alright. So if it's decay by 30%,
What is
means
that?
this part here is actually 30%.
You know, younger people they tend to do this when they
So
are free. They
decay
like to
2,
do this.
that means this part here is
It looks so
30%.
weird.
Yeah. I can't explain this. I can just read and I understand what it's saying. Because it's just 2 of I, right? I, decay 2. Yeah. Not very critical. So what happened that year is that I told the student, please read carefully. Very carefully. Please read again and read very carefully. I can't tell you is this 2, what it means. I can't tell you that.
Decay around 30.
Okay,
I just
it is what it is. So after 3 oscillations, you'll come to 30% of its initial value. Maybe I'll write it down here. This is also another way to word it. After 3 oscillations, the amplitude is 30% of its initial value. Okay, that's what it means. This one, 0.3 theta naught. So I can set it up. That means my theta at time equal to 0 is theta naught. Yeah.
Do you submit like that or in a proper
is
figure
at theta
paper?
naught. That's my first initial condition.
Like that.
The theta
I wonder if you know how to
time
write.
3 tau t
Doesn't matter.
is equal to
You can try to do
0.3
something
theta
on
naught.
the process paper.
Right?
Something
Why
like that.
3 tau t? Because this is the amount of time that it would take. Over here, 3 tau t. So we know that the amplitude, the decaying amplitude that you saw today, the decaying amplitude. This decaying amplitude we saw is given as theta naught e to the power minus zeta omega n e. That's the decaying amplitude. So if you put them together, that means 0.3 theta naught must be equal to theta naught e to the power minus zeta omega n e. Where this t over here is 3 tau d. 3 tau d. Right, that's the t. So Sanskrit was asking me, where is your cosine and sine term? Where are they? Well, actually we are looking at complete cycle here. So the complete cycle is this point over here. Your sine and cosine term will give you this intermediate point over here. And wherever is at this peak point, that is only that decaying amplitude. Only that. Because this one here, this will be equal to 1, this will be equal to 0. So 1 plus 0 is 1, and then you're just left with that if it's a complete cycle. So that's what it means. That's why this part here is actually not included at all. So now that we have this, simplify, and the tau d over there is 3 omega n. Tau d is actually 2 pi divided by omega d. Yeah. So 3 tau d, where tau d is equal to 2 pi over omega d. So omega d is actually omega n square root 1 minus zeta squared. So just in case if you don't know, it can be found in your data sheet. So in your data sheet, right over here. Yeah, omega d equal omega n square root 1 minus zeta squared. That's why I want you to know your data sheet very well and understand which question refers to which part of your data sheet. So this one is for the case response equation for free vibration is found under there. So after we have that, so this part here will be omega n square root of 1 minus theta squared. So this and this cancel. 6 pi, I'll bring it over here. But before I can do that, I need to take ln on both sides. Yeah, and then bring 6 pi here. So over the years, I also get to see that actually students don't know how to solve this. There's a zeta, there's zeta, one equation, one unknown. There's a square root over here, and then totally frozen. Don't really know what to do. And then give me a lot of working, and then it's all incorrect. So how to do this?
Is this the real one?
So if you work this out,
Is this the real one?
and then multiply by -1 on two sides, you get this to be zeta over square root 1 minus zeta squared
Because
equals
I put what here.
0.0639. Yep, you work it out. This one is all constant over here. And the next thing is to square both sides. Right, that's how we do it. So if we square both sides, this is squared, this is 1 minus zeta squared equal 0.0639 squared. And once you have that, you can multiply it in. Now surely you can, you'll be able to solve this one. So do that one. Zeta equal to 0.00406. Is there units for zeta? No. So you don't have to put down no units as well. So let's look at the marks allocation. So if your here is able to get this part,
And then the value is wrong.
kind of like understand this line, this part, 1 mark. If you're here, also understand this part here, substituting tau e and then omega e into it. This part gives you 1 mark. And after solving this, is 1 mark. So it's not the end yet. Yeah. This is question 6 marks. So some of you may have slightly different numbers because maybe this part here you wrote 0.064 squared. Right? And then that results in a slightly different number. These are all accepted, marked correct. Right? So it's okay to have different number of decimal places. There's no hard and fast rule how many decimal places you must use. Right? Sorry, this is for the square. So. I haven't taken the square root. Sorry. So if your friend got it right, just give him or her a thumbs up. So the next thing that we want, because the question wants us to find out what is the damping coefficient C. So in order to find that out, we'll do
Actually, I wrote it here, I
a
never see.
coefficient comparison. Comparing coefficients. is second order.
Shiva, I give myself a thumbs up.
That looks more like a.
So what do I mean by that? You can see that we have this form over here.
One day more,
This shown form.
another day, another
So what I'm going to do is copy that and put it down here. That was the shown form. So we know that this part over here, this is equal to omega n squared. This part here is 2 theta omega n. Right? So I think the question gave a lot of other values. So even m, that's 10 kilogram. Capital M, 15 kilogram. L, 1 meter. K, 100 Newton per meter. And it wants us to find out what is the depth information C. So let's calculate it. This omega n will be square root k over 7 over 3 m plus 9 m. So substitute all this in, your omega n should be equal to 0.795. And if your peer didn't add in radians per second, it's